in security, not like the one that we already seen before, which is basically a way to express information flow control properties. In general, a program with confidentiality concerns classify data according to confidentiality levels that are defined in a security lattice. This lattice also defines the way that data can flow inside a program. In a simpler setting, we can think in a program with high confidentiality input and output. And those output channels represent the way that a high security server and a low security server have to see the execution of the program. So the idea is that we want to reject invalid flows, such as those from high confidentiality data to low confidentiality input. Then the basic notion of non-interference is expressed on low sensitive equivalence, which basically equate any two private values but distinguish between low security values. So basically, a program is going to be non-interference if given two related input at the low level, we obtain two related output at the low level also. And ideally, non-interference is a modular property, so the developer can reason about the specific modules, and also it's very interesting from the meta-theoretical point of view. So one of the ways to control information flow is security typing. In a language with security typing, types are extended with security levels, which creates a new notion of security types that the data system uses to detect and reject invalid flows. By doing that, in most cases, we can state a soundness property that says if the program is well typed, then the program satisfies non-interference. But a sound type system and non-interference are too strict in practice. Even a simple loading function, which by design must release some information about the secret password, whether or not this password is equal to the user public input, is going to be rejected by the data checker. The justification is that any secret that is involved in a computation makes the computation also secret, and since we are returning here this value to a place where we are expecting a public one, we have an invalid flow. So the question is how to release information intentionally, and the answer is declassification. There are a lot of words on declassification. In this presentation, I'm going to talk about two of them. The first option is to use an arbitrary declassification operator, similar as the one that GIF has. GIF is basically a subset of Java within information flow control. And the declassify operator downgrades the security level of an expression. So we can use it to say that the equality comparison is going to be public. By doing that, the data system is going to be happy, but it's not sound now because this program does not satisfy non-interference. And the question now is, what is the security property of this program? Worse than that is that arbitrary declassification allows us to declassify the password itself, which is very bad. So the real question is how to have declassification while retaining a security policy. One of the problems with arbitrary declassification is that declassification is not part of the security specification. And in that sense, Lianes Dancewicz proposed a nice approach to include declassification as the security specification. Specifically, they use declassification policies, and those policies are part of the security labels. With that, the data system can track them and enforce them. And also, the data system can enforce a relaxed version of non-interference. In short, in that work, every secret has a declassification policy. For example, for the password of the loading function, we can declassify the password by comparing it with a public value. And this is specified by a function that takes the secret, and the body of the function is going to be the operation that we want to declassify. In that case, just the equality comparison. You can declassify multiple operations, and we call that progressive declassification. But also, a full secret value is going to have a declassification policy, and its specification is the constant function. In a similar way, a fully public value is going to be specified by the constant function. So those functions are part of a lattice on that word of Lian Stancewood, where labels are set of functions. And the root thing with this approach is that we have a very precisely way to express the classification for values, but also is very hard to reason about the lattice structure because it involves general semantic interpretation of functions. So our idea is to simplify that, but using type level policies instead of value level policies. The insight is that type interfaces can express the classification policies. Let's see how it is. For example, the top type interface, which is empty, represents any secret value in the sense that we don't have any method to see what is behind that type. And on the other hand, the fully typed interface gives us access to every functionality that the value has. In the middle, we have the interesting part. For example, we can express the password policy using this interface that defines an equal method, which authorizes to use the equality comparison that is implemented in the underlying object. And also, we can express progressive declassification by nesting methods and type interfaces. So, the root thing with that is those types are in a well-known lattice, which is subtyping, and in most cases is easy to reason about subtyping. So let's see if this idea protects us from the low security server and allow us to express the classification, in fact. For the logging function, instead of taking a fully secret password, we are going to take a password that has this string equals policy that allow us to use the ECOOP method so that the system can check and verify that we are using the policy in the right way. Also, if we have a full secret value and we try to use the logging function which is expecting something with a classification policy, the subtyping relationship is not going to hold, so the system can reject that very easily. And also, if we try to do something like return the password itself, the system subtyping again is going to do the work because there is no relationship between those types. The idea also works for the classification, progressive declassification, in the sense that with progressive declassification, we need to use all the change of method to get the public result. If we use, for example, only the hash method, we are going to get something that is not fully public. So if we try to return that to a place that is expecting a public value, we are going to have a type error also. On the other hand, if we use the policy in the right way, which is to invoke a hash and then the equal method, we are going to obtain a public result, and then we are going to be okay with the expected type. Also, one interesting thing with this idea is that it uses the power of the underlying type system, in the sense that, for example, if we have recursive type, we can have this list of a string type, and we can express policies that talk about, for example, that we can compare the element of the list with a given value. We can do that by abstracting the head of the list to the previous policy, which was a string equal. And also, we need to include operation to traverse the list, and especially the tail of the list is going to have the same policy that the whole list. So, from the perspective of the lower server, it's the idea works. So let's see what happens from the perspective of the high security server. And what we want is to support computation with secret data. Suppose that we want to implement a check function that takes a private or secret password, and it's going to return whether or not this password is written than 8. In a traditional programming language with security type, we can specify that the return type is a Boolean that is secret, and the parameter is a string that is secret. But with our approach so far, we just can put top on both sides. By doing that, we do not have a way to distinguish that we are going to return a Boolean and also that we are going to receive a string. Even worse, the len method does not have sense here because it's just a standard type error. So the conclusion is that one type is not enough for this idea, so we need security type in fact. So we introduce a new notion of security types, which is basically a facet type, where the face type and the first type is the safety type that basically is the one that the higher server uses. The other one is the declassification type. That is the way that we have to restrict operation for the lower server. This is the way that we write security types in this new language. So now we can write again the check function. We can receive, in fact, a string which is secret with the declassification top. And we can return a Boolean, which is a secret. And if now we find that a method is not in the declassification policy, we are going to look for this method in the safety type. And if this method is implemented there, we are going to take the return type, and we are going to change just the declassification policy to say that the underlying computation is secret, and this is going to be propagated the rest of the computation. If at the end we are expecting that, if we are expecting a Boolean secret, we are going to be okay. So with this notion of facet type, we can express our security property, which is basically a realized version of non-interference. So we define that security property using an observational equivalent on object. Basically, an object is defined by the observation that can be made on it, which is basically invoke is method. So if we don't have any method to use, we can say that both strings are equivalent because top has an empty interface. In a similar way, we can say that those strings are equivalent at the type string length, because string length just has the length method, and both strings has the same length. But on the other hand, if we have the full type, we can use some method in the type interface, for example, the method char_add, to realize that those strings are not equivalent. For example, the first characters are not equivalent. So we use that to parameterize our security definition, which is basically type-based realized non-interference. And we use two observational levels, one from the input values and for the output. The input observational level is going to specify the declassification policies for the program. And the output observational level, in most cases, is going to be the full type, but we can modify it. And the properties similar to a standard non-interference in the sense that a program is going to be type-based realized non-interference if executing the program with relative values at the input type, we obtain relative values at the output type. In fact, this specification of type-based realized non-interference is also modular. For that, we need more than one type at the input observational level. In fact, we have an environment with all the declassification policies for the variable in the program P, and that makes the program P an open program, so we can reason about any program with this property. Let's see how to use this property to see if a program satisfies our security property or not. For example, here we have an input observational level, which is string length. We have this program s.length, and we are expecting to observe the result at the int type. So, in fact, this program is secure because any execution of the program with values that has the same length, we are going to obtain the same length. So that's why it's secure. But if we change the program to that program .mary, and of course we need to change the return type because now it's going to be Boolean, but also it's a public type. Now we can realize that this program is not secure because if we execute it with relative values at the length level, we are going to realize that the results are not equivalent to at the Boolean type. So that is our security property for our declassification approach. Then, in the paper, you can find the formal definitions, in particular, the one for observational equivalence between objects that uses a step in the logical relation because of recursive type, but also you can find the proof, especially the one for the soundness property. Also, we have a discussion about how the system power increases the declassification policy power. We talk about what we can get with universal type and refining type. That's it. We are captured intuitive and expressive connection between type abstraction and the classification policy that allow us to be sound regarding our security property. Okay, that's it. Thank
you. Questions? Yeah.
Hey, very interesting idea. I was wondering, so this seems to work for objects where you have these types. Does this generalize to general values like integers or something like that? Because there you have not methods, but you have like and or plus or whatever.
Okay, we are assuming here a pure object-oriented programming model where all types, even those for built-in type, are a collection of methods. So we don't reason about the primitive type in a special way. No.
Okay. And then the second question would be, so basically what you restrict is what kind of functions you can use on certain objects, right?
Okay.
Did you think about what kind of, or whether it's still possible to do some laundering attacks to get more information out with these functions than you were thinking about?
Yes. In fact, by giving you the equality method, you can use recursion to guess the real secret. But our idea does not support that directly, but trust in the power of your type system to express that kind of thing. For example, with refining types, maybe you can be more specific about those kind of constraints, for example.
Thanks. This seems like a really interesting approach here. One of the challenges that I've seen, and my students have seen with information flow languages like GIF is the scalability is really challenging, right? The number of annotations you put in is overwhelming. It's very difficult to understand. Do you have, what kinds of programs have you written in your online interpreter? Does it give you any intuition whether it helps with this problem?
Okay. At this moment, we don't have solved that problem because you need to specify both types, but what we plan is to infer a minimal type for the program and give you the type definition, and after that you can change it a bit until to get what you want. This is the way that we have solved this problem.
So I don't remember if you mentioned that, but it looks like your types are structural, and it looks like that if they are supposed to fit into a nominal context, you would need to declare a lot of these extra similar types. They're similar except that they differ in their security properties. So is there anything essential in being structural, or what is the role played by that choice?
No. This was the setting that we choose to realize this idea, but we think that we can explore another ways. But having type interfaces with a structural type at least allow you, and you have a way to define inline types. It's just that not that is crucial for our idea.
But if you want 100 different types in a nominal settings, that should all be modified relative to existing types by having this eq property.
Okay.
You would have to repeat the same things 100 times.
If I understand well, you are asking about if there exists or not the operation that I want to declassify on the underlying type. Is that your question?
I couldn't.
Okay. I didn't understand well the question. I'm asking.
I expected that maybe you would need to write the same thing many times if you want to have a similar change to many types, such as all these types should be subject to this eq constraint.
Yeah, probably you need to write many times the same kind of types. And there isn't a space for refactoring tools here.
So a related question, if you wanted to allow leaking the first 3 characters of a string, so you can call char at, but only with arguments 0, 1, 2, and not with numbers larger than 2, how would you do that?
Yeah, with this, with the current development, you cannot specify that. But probably with, for example, with refining type, you can specify that by saying that the argument must be 0. I mean, the argument that you're going to spec is just 0. In that sense, you restrict the char at to be just 0, to expect just 0.
Okay, so let's thank Raimil again.